Begin. So my aim for today was we are going to begin with the rather easy questions. By easy, I mean those ones of determine the size of angle E1 if it is given that maybe angle A is 40 degrees and things like that. As well as those questions, find other angles that are each equal to X, things like that. Then from 7 p.m. when all the metrics are gathered here, then we can now begin looking at the proof type of questions. Prove that this is a cyclic quad. Prove that this line is a tangent to the circle at that point. Or this line is a tangent to the circle going through these certain points. So yes, we'll be looking at things like that. But just to quickly remind you of the theorems, well, just to say them, of course. I'm not really sure of the order, but I guess the order is not important. There is a theorem, which is the first one, that says if you have a circle and this circle has a chord, maybe let's say the chord is AB. Now, the perpendicular drawn from the center of this circle to the chord is simply going to bisect the chord. In other words, a line that is drawn from the center of a circle to this chord is going to bisect the chord, which means it cuts it into two equal halves, as he told us, Kumase. Well, I should have begun on page 1. Here I am. I'm actually on page 7, which is rather funny. So let's go to page 1. Right. I know it doesn't seem as if it's making a difference, but trust me, it does. Okay, now we are on page 1. We actually done that theorem. So you have a center, you have a chord, and this chord can be anywhere. It doesn't necessarily have to be where you see it. No. As long as you draw this line from the center of a circle, perpendicular to this chord, then you must know that it's going to bisect the chord. And as I told you, the chord could have decided to come here. And you still have a line that is coming from the center of a circle all the way to this chord. It will still bisect the chord. So I won't tell you about the converse of this theorem. I'll just say the theorem because we haven't got time to look at them into greater detail. And every time you use the first theorem, what is the reason you must give? The reason is line from center perpendicular to the chord. So that's the reason you must give. Well, of course, you know the symbol for perpendicular, so you don't really need to write it in full. You can simply say something like this. Just that finding the perpendicular sign on my keyboard is really a task, so I'm not going to do that. Okay. We also have a theorem that says if I have a circle here and I have a nice center, then what is going to happen? Well, I can actually have a chord or an arc. I don't really need a center in this case. No, I don't. As long as I have either a chord or an arc, and I have maybe a shape like this one. In this case, I don't have a chord, but I'm going to have an arc. So this theorem says every time you see a shape like this, you need to know that these two angles are equal to each other. Let's give them names. Angle A as well as angle B. Why are they equal to each other? That's because this arc subtends angle A at the circumference of a circle. And the very same arc is going to subtend angle B at the circumference of a circle as well. It could have been an arc or it could have been a chord. Both of these arc and a chord, they subtend angle A and B at the circumference of a circle. And since these two angles are subtended by the same arc or chord, then they are equal to each other. All right? And every time you use this theorem, the reason you must use is angles in the same segment. Well, this is an inequality sign, but let's assume it means an angle. So, yes, angles in the same segment. Of course, they are not the only ones. Even these two are equal to each other because they are subtended by this arc, sorry. Okay. There's also another theorem which follows from this one. But in order for it to be true, we must have a center in that case. What does this theorem say? It says, if maybe you have something that looks like this one, and something like that, then you need to know that in this case, we have two angles, both of which are subtended by the same chord, or rather arc in this case, sorry. It could have been a chord as well. That's still fine. But let's just say arc. This arc, let's call the arc AB. The arc AB subtends, which means it forms this angle at the center. And the very same arc is going to form this angle at the circumference of the circle. Let's give them names as well. Well, we like to say the center is O. So we call this angle O1, and we can call this one O2, but let's just label O1. So what you need to know here is angle O1 is twice as much. Maybe let's say this is angle A. That's what you need to know. The angle at the center is twice the angle at the circumference. That's what the theorem is saying. And every time you use this theorem, the reason you will give is angle at center is twice angle at circumference. So that's what you will say when you answer this, of course, in the exam. Okay. You also need to know that there is a nice theorem that says the following. What does it say? It says, once again, if you have your nice circle like this, and you have a center, such that a line that passes through the center of the circle, we call it the diameter. It can be any line really. It can pass this way, pass that way. It doesn't matter. As long as it passes through your circle, from one point to another on the circumference, then we call this line the diameter. What does the theorem say? It says the angle that is subtended by the diameter at the circumference of the circle, that angle will be 90 degrees, all right? And this theorem is actually a consequence of that theorem, which means it follows from the angle at the center, which is twice angle at the circumference. And I think you can make sense out of it. The angle at the center is the angle on a straight line, and this is 180 degrees. Now think of it. This chord, arc. What is wrong with me? This arc subtends the 180 degrees at the center of the circle. And the very same arc is going to subtend this angle at the circumference of the circle. So it's the same thing. but nonetheless, it's a theorem in its own right. And every time you use this theorem, the reason that you're going to provide is you'll say that angle is 90 degrees because it is an angle in a semicircle. What is a semicircle? The word semi means half. So yes, I just wanted to make it to make sense a little bit. So that's what you'll say. You'll say it's an angle in a semicircle, half circle. It will give you the 90 degrees. All right. There's also another theorem that you need to be aware of. What is that? Well, it says if we have your nice circle as we do in this case, and on this circle, you're going to have a quadrilateral. As Mamgwevo told us, well, this quadrilateral can really do anything. So we have a quadrilateral which is special. What makes this quadrilateral special? Well, it's the fact that the vertices of this quadrilateral, they all lie on the circumference of a circle. Now, every time you have such a quadrilateral, then you must know that we call this a cyclic quadrilateral or a cyclic quad in simpler terms. Okay. Now, there's three theorems. Is it three? Well, two actually, that come from this cyclic quadrilateral. What are those? Well, if we were to give these vertices names, let's say it's A, B, C, D. The first theorem says the opposite angles of a cyclic quadrilateral are supplementary, which means if you take angle A because it's opposite to angle C, things that are opposite are things that are looking each other in the eye. So yes, if you add these two angles, you get 180 degrees. And of course, these two are not an exception as well. So if you take angle D, you add it to angle B, well, you simply get 180 degrees as well. And every time you use this theorem, the reason that you use is opposite angles of a cyclic quad are supplementary, which means they add up to 180 degrees. That's the reason you use, all right? Now, what is another theorem still on the cyclic quad? And how do you know that it's actually true? Like it's the true identification of that theorem? Easy. It must be an extension of one of the sides of your cyclic quad. That's very, very important. I'll show you when is it not. You can extend on all sides. That's perfectly fine. But this is what you need to know. This theorem says an exterior angle of a cyclic quad is equal to the interior opposite angle. An exterior angle of a cyclic quad is equal to the interior opposite angle. An exterior angle of a cyclic quad is equal to the interior opposite angle. And every time you use this theorem, the reason you must use is this is an exterior angle of a cyclic quad. All right? However, you're not going to say, if I now have something like this, let's say this one was not there. And let's say you had a line which is doing something like this. You are lying to us if you say this angle is an exterior angle of your cyclic quad. You're lying. It's not an extension of this side. So that's how you identify it. All right? Okay. So how many theorems have we talked about so far? 6. We still have 3 more. Then we can get right into business. So let's give them a good look. So what does this one say? Well, it says, if you have a center of your circle, of course, any circle will have a radius. But now, you need to know that a tangent line, which is drawn at the point of contact, in other words, if you draw it here, then you need to know that this tangent will be perpendicular to the radius. And every time you use this reason, in fact, this theorem, you'll say the tangent is perpendicular to the radius. Of course, if you like, not really if you like, use this symbol instead of perpendicular. The tangent is perpendicular to the radius. Well then, since I'm running out of space, I'm just going to remove this, all right? There's also another theorem that says, if you have a tangent line, a tangent to the circle, all right, such that inside of this circle you have a very nice figure. Maybe let's say this figure decided to look something like this. It shouldn't necessarily look like this, and it shouldn't necessarily pass through in fact, the center. No, could have decided to do something like that. Now, there's a theorem that says the angle between a tangent to the circle and a chord. In other words, the angle between the tangent and the chord is equal to the angle in the alternate segment. And what is a segment anyway? We keep on saying angles in the same segment, angles in the alternate segment. What do we mean by that? We now understand what the word alternate means. It means these two angles, they alternate. So what is a segment? This is a segment, the portion that you see here. In other words, that space between an arc and a chord, we call it a segment. This is a segment. The space between an arc and a chord. This is a segment. A space between an arc and a chord. Now listen to the theorem. This is the first segment, yes? It's the segment in which the angle is between the tangent and the chord. But now we say it must be equal to the angle in the alternate segment. Yeah, more or less. I hope you got it. But of course, if you didn't get it, you don't need to forget about it. This is not the time to forget about things. Okay, this is the last theorem that you need to be aware of. And it's the one that Nosipo told us about. She said, well, this is how the theorem looks like. The theorem says that if two tangents are drawn from the same point, then those two tangents are equal to each other in length. That's what it means. And here we can see that these two tangents, they come from the same point, which is the point A. As long as they are drawn from the same point, then they will be equal to each other in length. Oh, I forgot to tell you the reason for this one. Well, here you'll just say it's tan chord theorem. But for this one, you'll just say it's tangents drawn from the same point, PT. So if you're doing computer, you know that points are denoted by the PT. Well, nonetheless, even if you're not, that's perfectly fine. That's an abbreviation for a point. So, yes. So as of now, we are still crawling, and of course, we'll walk and run. So, yeah. So let's look at this situation. What is happening here? Well, this is how the statement reads. I'm not going to write it, but of course, I'll tell you the most important things from the statement. So they say, in this diagram that you see on my screen, B, D, and C, they lie on the circle that is having a center O. And AB as well as AD are tangents to this circle at B and D respectively. Angle BAD is 59 degrees. So that's what we are saying. And that's all you need to know. You don't need to know the first line. It's something that you can see. You also don't need to know the second line as well. You can see that those two lines are tangents, but nevertheless, it's helpful for them to confirm that they're indeed tangents. So that's the first thing you really had to know. As well as the angle A there, it is 59 degrees. That's fine. Now, this is an advice that I give you. Before you even look at the questions, my high school teacher used to say, you are populating the diagram. In other words, you identify all the theorems that you see, which is the 9 ones that I just told you, and also anything which is not a theorem, but which can assist you. What do I mean by that? I mean an isosceles triangle, for instance, because it will tell you that angles opposite equal sides are equal to each other. So that's that. An exterior angle of a triangle, yes, it's not a theorem, but it can really, really assist you. There's also, guys, another theorem that you need to know, and it's the midpoint theorem. It was actually taught in grade 10, but they can ask you in grade 11 as well as in grade 12. So you need to know the midpoint theorem. I'll just quickly show you what does it say. You can actually state it in two ways. And this one applies when you have a triangle. It doesn't matter what kind of a triangle. It could have been a right angle triangle for all we know. Doesn't really matter what type of a triangle, all right? But then what does it say, this midpoint theorem? It says, this is the first way of stating it. In the first way, you are given parallel lines. And if we were to label this, the bigger triangle is ABC, and of course, this will be E. That's an ugly E. This is much better. So what does the midpoint theorem say? It says, a line segment passing through the midpoint of one side of a triangle parallel to another side bisects the third side. Hey, maybe I should write this one down, eh? Okay, I'll write it here. It says the line segment, well, A actually. Yes, a line segment passing through the midpoint of one side of a triangle parallel to another side. What does it do? It bisects the third side. In other words, two conditions must be satisfied in order for this line to bisect the third side. The first condition is it must pass through the midpoint of one side of a triangle. The second condition is it must be parallel to another side. And if those two are true, then it will bisect the third side. But that's not all. Oh, why doing this? This is the next part. And is equal half the third side. That's how it works. So it's an insertion here. It's something that is continuing. Please forgive me for that. What am I saying in simpler terms? Well, now you can see that DE is parallel to BC. That's the second condition. But also we can see that DE is passing through the midpoint of AB. Then this theorem says it's going to bisect AC. And Fumo told us that it means it cuts AC into two equal halves. And furthermore, this line is going to be half of this other side. That's what we are saying. And every time you use this theorem, the reason you must use is midpoint theorem. Terribly important. Okay, that's the first way in which you can state it. That's not all. We do have a second way. What does it say? Well, in this case, it says a line segment joining the midpoints of two sides of a triangle. This line segment is going to be parallel to the third side. It's actually more like a converse, but not really a converse. No, we can't really say it's a converse. It's another way of stating the midpoint theorem. In another way, yeah, it's another way. Or maybe we can say it's two midpoint theorems if you like. But yes. What does it say? It says, if a line segment joins the midpoints of two sides of a triangle, we can see that this line DE joins the midpoints of AB as well as AC. Then that line will be parallel to the third side. Not only that, it will still be equal half of the third side. So please note that. Terribly important, this midpoint theorem. Of course, we are going to apply it in today's lesson. There is a question that deals with it. Okay, let's begin. So yes, we said the first thing is to identify everything, all the theorems that we see here. Now, since we can see a tangent, let's go to the tangent line AD. According to the tan-chord theorem, we know that the angle between a tangent to the circle and a chord is equal to the angle in the alternate segment. That's the first thing we can see. But that's not all. The angle between a tangent to the circle and a chord is equal to the angle in the alternate segment. All right? Okay. Now we shift our attention. We go to the tangent AB. The angle between a tangent to the circle and a chord is equal to the angle in the alternate segment. And also, the angle between a tangent to the circle and a chord will be equal to the angle in the alternate segment. Okay, fine. Going to the tangents once again, we see that these two tangents are drawn from the same point, which means they are equal in length. And I really need you to pay attention because, of course, in the next question, I will be asking you questions. So, yeah, that's the niceness of it. And since we know that these two lines, or rather AD is equal to AB, then it means we now have ourselves an isosceles triangle. And if we have an isosceles triangle, it means that angle B1 is equal to angle D1. And the reason that you use in an isosceles triangle is angles opposite equal sides. Perfect. Then what else? Do we still have theorems here? Of course we do. What are those? We know that O is the center, which means OB is the radius of a circle. OD is the radius of a circle as well. And we know that a tangent is perpendicular to the radius. Well, maybe I should use this color, which means that angle OB, okay, doesn't have a name there, but that's fine. As well as angle OBA. Those two angles are 90 degrees. It's better to label OBA. Yes, or you can say B3 plus B4 is 90 degrees. Yes, that's actually true as well, because we don't have a letter here that we can use in order to give that angle a name. And of course, you now understand that's not all. This angle will be 90 degrees, and that angle will be 90 degrees as well. Okay, what else? Well, these two lines, they are the radii of your circle, radiuses, but we don't have such a word, radii. And of course, the radii are equal to each other, which means angle D2 is equal to B2 because we have an isosceles triangle. But it's also another theorem here. We can say that this chord, or this arc if you like, point is BD. It subtends angle O1 at the center. It also subtends angle C at the circumference of a circle. So, you know that thing. Angle at the center, twice angle at the circumference. Yeah, no, I think we can stop. Exterior angle, of course, it's there as well. Now, I think we have identified enough for this question. So now we can look at the first question. Try. Okay, so the first question here is asking us to please find the size of angle B1. And this is for 4 marks, imagine. So where is this B1 if we give it a good look? Well, I think my diagram is rather dirty, so I'll just clean it up. Hopefully I still remember the angles which are equal to each other. So yes, we need to find the size of angle B1. That's fine. But this is what we know. We know that if you take B1 and you add it to B2, you will get 90 degrees because we said angle OBA is 90 degrees. Right. Now, it's really gonna be easy if we know what is the size of angle. Okay, no, we don't need it. We don't. We can just go to this triangle and get straight to the point, this one. Yeah, that's what we can do here. How do we get straight to the point? This is what we know. We know that if we take angle A and we add it to angle B1, and we add it to angle D1, the result is going to be 180 degrees because it's a normal triangle, right? So it's because of the sum of interior angles of a triangle. That is what we know. But then there's something that we also know. What is that? We know that angle B1 is actually equal to angle D1. We know this. Now, why do we say B1 is equal to D1? Well, that's because they are angles opposite equal sides. Because of this isosceles triangle. Oh, by the way, before you say this statement, I really believe that you need to tell them that you realized this is an isosceles triangle. How? By telling them that the length of AD is equal to the length of AB because they are tangents drawn from the same point. Yeah, we should have begun with this statement, really. So let's call it step one. Convince us that you fully understand that these two lines are equal to each other. And now we have an isosceles triangle. Then now that you have told us this, tell us that you are now focusing in this triangle. And if you add all these angles up, you get 180 degrees. But thirdly, you realize something. What is that? It's the fact that B1 is equal to D1. And of course, that's because they're angles opposite equal sides. So what you're saying is, if two tangents are drawn from the same point, then I'm going to have an isosceles triangle. And in an isosceles triangle, the base angles are equal to each other. That's the argument you are building here. Okay, so what? Remember, you are looking for B1. So now you can choose to express angle B, or at least angle D1 in terms of B1. That's what I should have said. In other words, where you see angle A, you put 59 degrees, but where you see B1 plus D1, knowing that they are equal to each other, it's like you're having B1 plus B1, which is twice as much angle B1. That's what you can say. Then you can say this is set equal to 180 degrees. And now you can get straight to the point and tell us what is B1. So you'll just say it's going to be 180 degrees minus 59. Then you get 121 degrees. And now you divide this by 2. Then you find that the size of angle B1 will be 60.5 degrees. Yes. It's really powerful what you just said here. B1 is equal to D1, which means where I see B1, or rather D1, I mean D1, 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 you can choose to express it in terms of B1. So yes. So going to the next question, and this is actually for 3 marks. They say, please determine the size of angle O1. All right. Where is O1 anyway? Well, this is O1. Now here you need to connect the dots, and you really need to have that skill of moving from one figure to another. So now we are moving from a triangle. We are going into the circle. because O1 is one of the angles that form the center of the circle. And I really hope you're not going to say this is a cyclic quad, because clearly angle A is way outside of your circle. So it's not lying on the circumference of the circle, sorry. So what's the best way out? Remember, you now know what is B1, yes? You can use B1 in order to find B2. And since you know that these two sides are equal to each other, then it stands to reason that these two angles are equal to each other as well. Then you can use the sum of interior angles in order to get O1. That's a way that I think you can use. It's not the only way, of course. There's many ways to kill a cat. You just need to find the one that you prefer and get it over and done with. You could have used angle at the center, twice angle at the circumference. It would have worked as well. But before you use that, you are going to say this angle is equal to that angle. Now you know the size of angle C. Then you know that this one is actually twice the one at the circumference. Many ways of killing the cat, but I think this one is the quickest way. Yeah, no, it's really the quickest way out. So let's use that. What are we saying? We are saying angle B1 is actually equal to angle C. You can also tell us that both of them are equal to 60.5. And this is all thanks to the term called theorem. Okay, so now we know the size of this, but we also know something else. We know that angle O1 is actually twice as much angle C. So you can even go on and say it's twice as much 60.5. Well, that's because the angle at the center is twice as much angle at the circumference. Well, you'll write it in full. Please don't write circumf. Write it in full. Then now you can conclude and say, well, this means that O1 will be twice as much, which is just going to be 121 degrees. So yes, you could have really said that. This is the shortest way. Instead of beginning by saying B1 plus B2 is 90 degrees, because the tangent is perpendicular to the radius. All right. Then you can find the size of B2. And now that you know B2, then you say, but we know that B2 is actually equal to D2, angles opposite equal sides. Then you can take B2 and add it to D2 and add it to O1 and set this equal to 180. The sum of interior angles of a triangle, then you can find O1. So you decide which way is the best in business. Of course, those are not the only two ways, possibly. It's possible that there's another way that you saw, which I didn't saw. That. Yeah, I always like to reference, when ideas don't come from me. So I hope you don't feel offended, but that's how it is in the academic world. You learn that when you get to university. What am I saying? I'm saying, according to Nja Pase, he's saying we can actually prove that the quadrilateral ABOD is a cyclic quadrilateral. Let's say a question were to say that. So what are we going to say? This is what I need you to know. If you must prove that a quadrilateral is cyclic, you need to show us that at least one of the three things. Now, what is the first thing? Did you know that if we can show that two angles are in the same segment, in other words, if we can show that two angles are subtended by the same arc or by the same chord, then you have actually proven that a quadrilateral is cyclic. Imagine. Let's go back to this figure and remove the red. Did you know that if we can prove that angle A is equal to angle B, then it means ABCD will be a cyclic quad? Well, that's true because if I were to join these together, then it's now a cyclic quad. So it's one of the things that you can do. Show us that two angles are in the same segment, or you can show us that an exterior angle of this quadrilateral is equal to the interior opposite angle. If that is true, then this is a cyclic quad. Well, that's not all. What is another thing you could have done? Well, if we can show us that when you add two angles, which are opposite, of course, if you get 180, then yes, that is a cyclic quad. And in this case, that's the condition we are going to use. We focus on the blue quadrilateral. And if we have to show that it's a cyclic quad, that's easy. What are we going to say? According to Njapase, he's saying angle ADO is 90 degrees. That's true because a tangent is perpendicular to the radius. And also, angle ABO is 90 degrees as well. For the same reason, tangent perpendicular to the radius. Then what? Literally add those angles because we need to see at the end of the day. So show us that if you take ADO and you add it to ABO, where it's going to be 90 plus 90, which is 180. Now we have literally seen the sum of these two opposite angles of a quadrilateral add up to 180. Now you can conclude and say, this means that ABOD is a cyclic quad. You need to give a reason. Why do you say it's a cyclic quad? Well, you can just say, I'm using the converse of opposite angles of a cyclic quad. Yes, you could have used this reason, or you could have said opposite angles of a quadrilateral are supplementary. Yes, because the converse says if those two opposite angles add up to 180, then this is a cyclic quad. But ideally, I think easier reasons are the ones where you begin with the converse. Converse of this theorem, converse of that theorem, converse of that theorem, and then you're fine. But of course, it's not the only way. The shortest way out was to observe that this is 90 degrees and this is 90 degrees. So in this case, well, you just have to say B3 plus B4 is 90 degrees because the tangent is perpendicular to the radius. Then tell us that B3 plus B4 is actually equal to angle ADO. Of course, we have seen that they're both equal to 90. then conclude and say, this means you are having a cyclic quant. And what would be your reason in that case? Converse of exterior angle of a cyclic quant. Yes, but let's not worry about it that much for now. We'll see it in due time. But yes, that's good thinking. Thank you so much, sir. Good to go. Okay, so this is how the statement reads. They say, in this diagram that you see on my nice screen, O is the center of the circle passing through the points A, B, C, and M. All right. Then they say K is the center of the circle, which is not drawn. But this circle is passing through the points A, B, and C of triangle ABC. Okay. Yes, just to get that one again, they said K is the center of the circle which is not drawn, but which is passing through the points A, B, and C, the points which are on triangle ABC, such that K lies on radius BO. Okay? And then they say angle A1 is 30 degrees. And BO bisects ABC. And that's what they say. BO bisects ABC, which means that angle B1 is equal to angle B2. That's the meaning of the word bisect. But remember they told us that K is the center of the circle which is not drawn. But they don't just tell you that, I don't know for what. It's not just for fun, you know? So please do sketch that circle yourself. So we know that this circle is passing through the points A, B, and C. And it's having the center at K. Well, we have something like this one because we really do need to make sense out of this piece of information they give us. I strongly believe it's not just for sports, but nonetheless, this is what we have. Okay, we tried. Right. Let's see what does it imply. What can it tell us? Let's begin there first. Well, this is what it actually means. Think of it. It means A as well as C are on the circumference of this blue circle. And yes, the point B must be on the circumference of the blue circle as well. Well, I know it's not a circle anymore, but rather an ellipse. An ellipse, I mean, but more or less, yeah, that's how it looks like. So what does it mean? Does it mean anything if K is the center of that circle? Well, I know. No, because anyway, AC is the diameter of the blue circle. That's true. But then again, okay, no, it does tell us something. AC, no, I lied to you. AC is not the diameter. It's not going through the center. So, no, it doesn't really tell us anything except that KO is equal to BK. Yeah, I think that's the only thing it tells us. Well, nothing else. No, not as far as my eyes can see. So it means we'll just get rid of that blue circle. That's fine. So let's begin our analysis. We know that the first thing we need to do is to identify all the theorems, as well as anything which is not a theorem, but which is helpful, of course. Now, first things first, we see a cyclic quadrilateral here, But then we are not going to have angles in the same segment in this case. No, we are not. However, this chord subtends angle O there at the center, and the very same chord subtends angle A1 at the circumference of a circle. So we know that this angle is twice as much, angle A1 there. What else do we know? Well, we know that these two are equal to each other because they are radii of the circle, which means that angle B2 is equal to angle C1. And that's actually all I think that I see in this case. It's really all that I see. Oh, they also said something. They said the size of angle A1 is 30 degrees. All right? Well, that's fine. Then what is the question asking from us? They say, please determine the size of angle B1. And this is for 5 marks. And I need you to know that in Euclidean geometry, they don't even need to tell you that giving reasons for your answer. No. Almost every statement you make, well, every statement actually, it must be supported by a reason. That's Euclid's geometry. Okay, let's begin. We know that B1 is equal to B2. That's what we know. It's given to us. They said BO subtends angle ABC. But then how can we find B1? Well, the key is to find B2 first. And how do we get B2? By finding angle BOC, angle O there. That's really the key. So let's follow that. We begin by saying angle BOC is twice as much angle A1. Then we give a reason, angle at the center. Yeah, you know the thing. Is twice the angle at the circumference, which means that angle BOC is simply going to be 60 degrees. Now what? Well, we know that BO is equal to OC because they are radii, even though it's obvious, but I strongly feel the necessity to tell them. I always like to write as if whoever I'm writing for is not a maths teacher, so I become as detailed as I possibly can. Okay, if those two sides are equal to each other, then what does it mean? It means that angle B2 will be equal to angle C1 because they are angles opposite equal sides. Well, this is what we say. Now then we can go to the triangle and say, when we take angle BOC and we add it to angle B2 and we add it to angle C1, we are simply going to get 180 degrees. This works best if you took this statement and put it there, and then take this one and put it there. But the order is not really so important, but it makes logical sense when you begin with the last statement and then say, but we know that B2 is equal to C1. Nonetheless, what is BOC? It's 60 degrees. What is B2? Yes, I'm now going to say twice as much B2 because those two are equal to each other. and the result is set equal to 180. Then I can make B2 the subject, but I need to give a reason why I say this, of course. That's because the sum of interior angles of a triangle is 180 degrees, right? Then what is B2? Easy. 180 degrees minus 60, you get 120. And when you say 120 divided by 2, you find that B2 will be 60 degrees as well, which means this is not an isosceles triangle. It's actually an equilateral triangle, but you are not given this initially. So it's still an isosceles until you actually do your work and find out, oh well, it's actually that. Nevertheless, we now know B2, so we can now say, well, B1 is equal to B2. It was given to us. You can say given, or you can say BO bisects ABC. You decide. And now you can conclude nicely and say, oh, well, it means my B1 will likewise be 60 degrees. Okay. What are we saying in this case? Well, here is saying we need to prove that angle M is twice as much angle A1. In other words, prove that angle M is 60 degrees because we now know what is A1. Where is angle M anyway? Well, this is where angle M is. Now, the first thing we need to ask is, what connection do we have to M1? Well, we know that M1 is one of the angles on the cyclic quadrilateral. And we know that if we take M1 and we add it to angle B, well, the result is 180 degrees. So that's what we are going to say here. We say, okay, fine, when we take angle M and we add it to angle ABC, I'm really going to respect it and not just say angle B because it's broken into two angles. The answer is 180 degrees. And every time you use this theorem, you'll see its opposite angles of a cyclic quadrilateral. Well, this is what you will say. All right? Well, then, this means M plus 120 degrees will be set equal to 180. Then M will just be 60 degrees, which is just twice as much. Angle A1. So yes, or if you liked, you could have said it's twice 30 degrees, but it's not really necessary. If you show us that it's 60 degrees, then it stands to reason that it's twice as much angle. Twice as much 30 degrees is what I wanted to say. So this is what they say to us in this situation. Well, they say to us in this diagram that we can see, O is the center of the circle, with the points A, B, and C lying on the circumference of the circle. All right? You don't need to know that, you can see it. Nevertheless, BAC, angle BAC, is equal to x. Why is that? BAC, in other words, this angle here, it is equal to x, and furthermore, OBC, OBC is x over 3 degrees. Then they say, determine with reasons the value of x. And this is for 6 marks. Okay. We don't want many things from you. We just want to know the value of x. So I think it makes perfect sense for me to ask a volunteer to please tell us which theorems do you see in this case. Just the theorems. I see this theorem, I see that theorem. I also see this thing which is not a theorem but which can assist us. Please go ahead, volunteer, and destroy this. Of course, if there's no volunteer, I can always choose a person. So we do it the easy way or the hard way. Yes, sir.
So I can see angles at the center is 5 angle of circumference.
So what's the angle at the center, sir? What is the name of that angle?
It's half of x.
The name of it, sir. The name of the angle.
I mean O, sir.
Yes, sir.
EOC.
BOC. You say BOC is twice angle A. Okay, sir. What else do you see?
Said angle OBC is equal to angle OCB.
And what's the reason, sir?
It's opposite sides equal angles.
Yes, sir.
Opposite sides equal angles.
Opposite sides equal angles. Are you sure, sir?
Yes, actually OP is equal to OC, and that's the rate.
Okay, fine. Okay, sir. No, thank you, sir. Those are the only two things in this situation, really. It's the theorem that you just identified as well as the isosceles triangle. So yes, thank you, sir. Okay. This is what we can say here. So what we can do is to work within triangle BOC. That's the best way to find the value of x. In other words, we'll begin by saying angle BOC is twice as much angle A, which I can say it is now 2x, because angle at the center, of course, it is twice as much that at the circumference. So now we know that this one is 2x. But there's something that we know, which is what you said. So you just said to us, angle OBC is equal to angle BCO. And of course, both of them are x over 3 because they are angles opposite equal sides. Well, you'll write the official reason. You've seen how it works. Angles opposite equal sides. These angles are equal to each other because they are angles opposite equal sides. Okay, fine. So now we have our x over 3 here. Then it's now easy. We now say, if we take BOC, we add it to OBC, which in turn is added to BCO. The result will be 180 degrees. I think this reason we've been using it as early as grade 8. the sum of interior angles of a triangle. You should be happy with it now. Okay, so 2x, which is added to x over 3, which is also added to x over 3. So I can just add those two up and say 2x over 3, and this is equal to 180. You can press this into your calculator and say 2 plus 2/3, and you'll get a beautiful answer, which is just going to be, so we times this one by 3 over 3, we get 6x. So we simply have 8x over 3, and this is set equal to 180 degrees. And writing degrees is very, very important. Some people, they just say equal to 180. Well, if I was your marker, I was really going to, yeah, you know the thing. Not because I don't really like you or want, but because you're doing maths in a rather funny way. Okay, now we can cross multiply here. Is it really 8? My mental math is funny, guys. Oh yes, it is supposed to be 8/3. So when we cross multiply, we say 8 multiplied by 1, we get an 8x. Then we say 3 times 18. Well, we get 540 degrees. And of course, we can now divide both sides by 8. So when you say 540 degrees divided by 8, you can't leave your answer as 135 over 2 degrees. What are you saying? Do you have 135 over 2 on your protractor? Because remember, an angle is measured using a protractor. So you can't really say this. So you need to be practical and say it must be in decimal. Right. I know in maths we like fractions, but in other cases, you really can't leave this as a fraction. Because what's the meaning of that? Okay, so this is what they say in this case. What are they saying? Well, they say to us P, Q, R, and in fact, P, Q, R, S, and T. Yes, they lie on a circle with center O. That is true. And then they say PR is perpendicular to OQ. This is OQ. And that's what they said to us. That's true. And these two lines, they intersect at F. In other words, PR as well as QO, they intersect at F. That's true. And then they say POT is a straight line. And then angle P1 is 42 degrees. Well, this is what they say to us. So I'm just going to appoint a grade 11 learner, a volunteer in fact, to please go ahead and tell us which theorem they see in this case. As many as your eyes can tell you. Yes, I'll allow a volunteer to go ahead. Of course, if no one volunteers, you know the drill. So this is the moment to shine, volunteer. Okay, no one volunteers. That's fine. So, what do you think, Mamukwevo? What do you think? Which theorems do you see here?
These are also cyclic quad. And then
What
there
is the
is
name of that cyclic quadrant?
so I forgot the name. And
No,
there's
the name
also
of the cycle
a
is
semicircle.
PQRST. That's the name of
Oh,
the cycle. So what's the name of the cyclic
so
quad?
so it's PQRT.
PQRT. Okay. Yes, I'll see. You may go ahead.
And there's also a semicircle, which is PRT.
PRT is a semicircle. So what do you know about a semicircle?
So it has R1 basically has an angle of 90 degrees.
Which one is equal to 90? Which angle is that?
R1.
Angle R1 is 90 degrees, okay?
And
What
then
else I'll say?
so that's all I see so far. And
Okay.
yeah.
Thank you, Jose. So, since no one volunteered, and it means I must ask another grade 11. Hopefully they didn't run away. Well, they actually did, you know. It was only you, Elsie, who's remaining. Nevertheless, we'll get them. Okay, what about you, Garabo? What do you see in this case? Except the angle in a semicircle and a cyclic quad, what else do you see?
Um, the theorem line from center.
The theorem line from center. Okay, I'll see. You are right. Thank you for that. Is there anything else that you see? Okay. So is there anything else you see, Nosipo?
No, sir.
Nothing. What about you in Japan?
So I see that angle Q1 is equal to Q2 and Q1 when you combine them.
Angle, what is it?
Q1 is equal to OPQ.
Angle Q1 is equal to angle OPQ. Okay, what's the reason for that? This one?
Where we have opposite in, I mean, we have the radius which is OQ and OP and they are equal. So we have an associated triangle.
Okay, so this is the radius and that is the radius, which means Q1 is equal to that. Thank you, sir. Anything else that you can see? Okay. Oh, you're saying something, Gagabo. Go ahead, Alcima.
So I'm not sure, but is T2 not equal to P1?
T2 equal to P1, and what would be the reason for that?
Um, Q is bisecting PT. I don't-
But bisecting, also, you can't say bisecting, they're much further away from each other, P1
I
and
think
T2. Okay. Maybe you can think about it in the meantime. Jaffa, so your hand was up.
No, so it was a lie. It's fine.
Sorry, sir?
So I didn't read nicely. I thought R1 is equal to Q1, but they are not substituted by the same code, so it's wrong.
Okay, sir. Okay. No, thank you, sir. Also, if you can give it a good look, this chord PQ subtends this angle O here, and the very same chord subtends this angle. So angle at the center, twice that at the circumference. But yes, thank you so much everyone for destroying this one. Well, of course, it's not always possible to see everything when you first give it a good look. So maybe it will take some questions to keep you a bit so that you can go back to the diagram and try to look closer. Nevertheless, let's go ahead. Now, this is what the first question is asking from us. They say, please determine the size of angle R1. And this is just for 2 marks, which means you don't really have to work a lot. Okay. Well, this is what who told us this. Yes, Ndozo told us this one. So angle R1 is 90 degrees because it's an angle in a semicircle. I heard someone saying it's an angle in a semi. Yeah, no, people are using a British accent, which is nice. Okay, so that's that. 2 marks, and then you're fine. Next, they say, please determine the size of angle S, and this is for 2 marks. Where is angle S anyway? Well, there is the green angle. This is where angle S is going to be. All right. So how do we get to S? Konje who told us, yes, it's Mamkwevo as well. She said to us, this is a cyclic quadrilateral. To look at this cyclic quad, which is true, that is a cyclic quad. But if you only identify that one, then you are really, really in danger. There is another cyclic quad, which is this one. So please make sure that you identify everything. Before looking at a question, try to get as much as you can from the diagram. All right? So knowing what we know, then it means angle S is opposite angle P1, which means if you take angle P1, you add it to S, you get 180 degrees. Because they are opposite angles of a cyclic quad, you'll finish this. Now, since we know that P1 is 42 degrees and S is unknown, then it stands to reason that angle S is simply going to be 138 degrees. No, I'm not entirely sure, so I'll press this into my nice calculator. Well, it is 138. And this calculator was given to me back in 2019 when I was doing grade 11, and it's still fully functional. Well, though I need to motivate it from time to time in order to work, I fortify it. Do you know what is to fortify it? I comfort my calculator so that it works. Yeah, it means I need to give it a bit of a push, but it's still functional. Sometimes it forgets that it's a calculator and slips. So I have to Right. Then what is the next question? Well, the next one is actually for 3 marks, and it's asking for the size of angle PQR. Where is that anyway? Well, this is P, this is Q, and this is R. In other words, the entire angle here, and that's for 3 marks. That's fine. So how can we get to this PQR? Well, if we look at this angle, it is in the cyclic quad that was identified by Mamukwevo. So it's all good. It means if we can find, okay, fine, I'm lying to you because we still don't know what is P2. So if we knew what is P2, then we only needed to find T2. And then we can just say opposite angles of a cyclic quad. But in this case, we don't know it. But then we also know that, okay, no. I'm cooking you. We found the size of angle S, didn't we? Of course we did. But then S is in a different quadrilateral, okay? What if we found T2? Well, we'll still have to find T1. Yeah, we'll still, but not really. No, let's find T2. Let's find T2. So how can we get T2? By using the sum of interior angles of a triangle. Yes. And then use the cyclic quad which was identified to us by Ndozo. So let's go. We say, if we take angle R1, we add it to angle P1, we add it to angle T2, well, the result is 180 degrees. Sum of interior angles of a triangle. Now we know that R1 is 90, P1 is 42. We are looking for T2, but the result is 180. So now we can make T2 the subject of the formula. And it's simply going to be 180 degrees minus 42 minus 90. Then we find that our T2 is 48 degrees. Sorry about that. Okay. So now that we know this, then it's easy. We now know that if we take angle T2 and we add it to angle PQR, then the result is 180 as well, because these are opposite angles of a cyclic quad. But now we know this one is 48 and this one is PQR. Then now we can gladly find the desired PQR. So it's also going to be 138 degrees. In fact, 132. No, it can't be 138. Okay, I thought I was seeing something, but I'm not seeing anything. So yes, it's 132 degrees, and then we should be fine. What is the next question saying? I'll just go ahead and fill everything up. In fact, we don't even need the angles in this case. Okay, that's even better. Yes, what is the question saying anyway? Well, the question says, they give us a few things. What's that? They say, if it is given that the length of PR is 7 centimeters, the length of QR is 4 centimeters, please tell us what is the length of QF? And this is just for 3 marks, all right? Okay, fine. Where is this PR anyway? Well, this is PR, so I'll just denote it by red. Yes, there is PR, and the length of PR is 7 units centimeters, that is to say. Now, what about QR? Well, this is where QR is. I'll just use turquoise to denote this. And the length of this one is 4 centimeters. Now they're looking for QF. Where is QF? Well, let's go and find it. This is QF. All right. It's easy to get QF. It means we simply need to focus on this small right-angled triangle and just find this side. But of course, we are given the whole length here, so we need the knowledge that Garabo gave us. So that's how we begin. How do we begin anyway? We tell them that PF is equal to FR, and both of them are equal to 3.5 centimeters. Why? That's because the line from the center perpendicular to the chord is simply going to bisect the chord. So now we know that this one is equal to that. Okay, fine. Then we can focus on FR and use the theorem of Pythagoras. And I always like stating the original principle. So I say the square of the hypotenuse is equal to the sum of the squares of the two other sides. That's what Pythagoras said. And of course, every statement you make, you've got to account for it. So that's that. Then now we can say, well, this means 4 squared must be equal to QF squared. And this is added to FR squared. So what's QF? Easy. No, I'll just go ahead. So I go to my nice calculator and I say it's the square root of 4 squared minus 3.5 squared. And here we are really going to get a decimal. So we'll just write it to 2 decimal places, and it's going to be 1.94 centimeters. Yes, unless if they said leave your answer in simplest sad form. So if they said that, then you're going to say it's square root 15 over 2. Yes, but if they didn't, yeah, no. It's always nice if you give it to us in centimeters. In decimals, that is to say. So this is how the statement reads in this case. They say, in this diagram that you can see on my nice screen, AC and CE are tangents to the circle having the center O. Well, this is the center of the circle, but I chose not to write it because anyway, O is not playing any role. We can see there is nothing that is connected to the center, so it's the same as if the center is not there. Okay. Then furthermore, they say B, D, G, and H are points on the circumference of the circle. HG is extended to the point F, that's true. BD is equal to BH, and D1 is equal to D4, and both of them are equal to X. Right. Then this one I'm going to give it to you, Pemelose, to please go ahead and tell me all the theorems that you see in this case. You can give it a good look, sir. That's perfectly fine. I'll give you 1 minute to carefully consider it, and then you can answer. Okay, so I think the minute has passed.
So I see tangents from a point with the line EC and AC. I see exterior angles of a cyclic quad. I see that's most of what I see.
So listen,
That's most of what I see.
most. So it's not all of what you say. So it means you still see something else. What is that, sir?
Mm,
Yeah, you did that yourself. So you said most. So I must ask for the rest. So.
okay.
Okay, so no, I think you had your fair share. Thank you so much, sir. You're actually right. So tangents drawn from the same point. What do we know about those two tangents, sir? What is special about them if they're drawn from the same point?
they equal.
Oh, they're equal, sir. Does
Yeah.
it mean AC is equal to CE? Is that what it means, sir?
Yes, sir.
Are you sure, sir? Even if I were to extend this one and do it like that, are they still equal, sir?
No. That means that BC would equal to CD if I'm right.
Thank you, sir.
Mm.
Okay, sir. Okay, sir. No, thank you, sir. Right. So what about you? Um, yeah, no. I think I'll give it to you, Garabo. What else do you see here apart from those two that the gentleman spoke about?
So I think the tan chord theorem.
You see the tan chord theorem. So which two angles are equal according to the tan chord that you see?
Angle H. Yeah. Yeah, I'm not sure. Say.
So how did you think of the tan chord theorem, Elsie? If you can see angles which are equal according to it.
What? Again, please repeat.
Okay, no, that's okay, Elsie. That's okay. Thank you for trying. Any idea, Ndonzo?
No, sir.
Sorry?
No, sir.
You don't have an idea. Okay. Nosipo, what about you?
So I see that angle D1 is equal to H1 because of the 10 chord theorem. And angle B3 is
Okay.
also equal to H1 because of the 10 chord theorem.
Angle B3 is equal to H1. Okay.
And angle A1 is equal to D2 because of the 10
A1
chord
also.
theorem. A1 is equal to D2.
Are you sure?
Oh, wait. So I said D1 is equal to D2. Can I say that?
Okay, I see. Yes, if you say that, it's true.
And also said D1 and D2 are equal to G1 because of the 10 chord theorem.
Angle between a tangent to the circle and a chord. Angle in the alternate segment.
And also D4 is equal to H2 because of the 10 chord theorem.
Okay.
Yeah, I think that's also.
No, it's not all, I'll say. Stretch your eyes a bit more.
Oh,
On the same concept.
and there's D3 and D4 is equal to B2.
Is it really equal to B2? Yes, I'll say it is equal to B2. Thank you so much for that. That's the angle between a tangent to the circle and a chord. And this is equal to the angle in the alternate segment. So there are many tan chord theorems in this case. Okay, thank you everyone for your participation. I really appreciate it. Okay, now that we have exhausted the diagram, then let's go to the questions. So, what are we saying? Well, the first question says we need to find four other angles that are each equal to x. That's fine. Except that D1 is equal to D4. No, it's given to you that one. So our duty here is to find four other ones which are equal to x. Fine. So according to the tan chord theorem, we know that angle D1 is equal to angle H1. Yes, that is true. And of course, both of them are equal to x for the reason I just mentioned. So you'll write the theorem there, okay? And also, angle D4 is equal to angle H2, and both of them are equal to x. For the same reason, tan chord theorem, that's true. Yes, it is true. It is true. Also, we know that angle D1 is equal to angle B3, and both of them are equal to x because they are angles opposite equal sides. You'll finish the reason, of course. And once more, okay, now B3 and H1 are already equal because, yeah, I should have said H2 there. Sorry about that. Okay, that's what we are saying. Now, what else is happening here? Which other angle is equal to x? Well, D2, we didn't say anything about D2, but it's also equal to x because H1 is equal to D2. and both of them are x. For the same reason, angles opposite equal sides. Yes, that's because BD is equal to BH, so then it stands to reason that those angles are equal to each other. So these are the only ones I can see, but it's possible that there are other ones as well, of course. Angle B1 is also equal to x because it's equal to D2 now. So if they wanted five angles, then you can also say B1. Yes, it will be equal to D2, which is x. Yeah, no, I think we can put it to rest. Okay, fine. Then the next question says, hence or otherwise. Hence or otherwise, prove that BD is parallel to HG. That's what they say. And the word hence means you use what you found previously, what you found above, in order to make this, or rather in order to do this question. In other words, we are going to go to this piece of information which we found in the previous question and try to see how can we prove that BD is parallel to HG. Firstly, let's identify those two sides. I'll use turquoise in order to identify them. Where is BD? Well, this is BD. And where is HG? Well, this is HG, right? Now, I'm just going to ask a question here, and a volunteer can answer us. How do we prove that two lines, are parallel to each other? What is the concept that we have to follow? Volunteer. Yes, sir.
So you can prove that the alternative angles are equal because a co-interior angles are supplementary and so there are no corresponding angles in this case. So I think that's also.
Okay, sir. So in this case, you're saying we can prove that two angles alternate. In other cases, we can also prove that two angles are corresponding. And in other cases, we can prove that the sum of two angles is 180 degrees, which would then mean co-interior angles are supplementary, and therefore the two lines are parallel to each other. Thank you so much, sir. Okay, so here we can see a Z shape. So if we can prove that angle D2 is equal to angle H2, then we have proven that BD is parallel to HG. And as a matter of fact, we have already done that. We just said H2 is X. We also said D2 is X. So now we just need to write down a conclusion, or rather an observation first. What is the observation? The observation is D2 is equal to H2. That's what we can see. And both of them are equal to X. Well then, this means that BD is parallel to HG. You are proving parallel lines here, so you've got to give a reason. Why do you say they are parallel? Well, that's because the alternate angles are equal. So that's the reason why. Yes. Thank you, sir. And let's finish this. What is the last question saying? Well, here they're saying prove that angle G2, show that it is 180 degrees minus 2x. And this is just for 2 marks. So where is G2? The exterior angle of a cyclic quad. All right. Now, we need to find B2 first, the size of angle B2. That's the easiest way to get to G2. And how can we do that? Well, this is how we can do it. Yes, this is how we can do it. We can say, if we go to this turquoise triangle, well, this one, then what is happening in this case? Easy. When we take B2, we add it to D2, we also add it to H1, the result is 180 degrees. You know the reason. Now, this is x and this is x, so that's 2x. And if we take this to the other side, we get 180 degrees minus 2x. All right? But now we know that G2 is equal to B2, and it will now be 180 degrees minus 2x. Why? Well, that's because it's an exterior angle of a cyclic quad. So yes, that is that.